2 of Fort Collins Comic-Con and our science stream. Yesterday we had some really good talks. Today we're going to continue that tradition. And this morning we have Dr. Claire Raftery, and she's Director of Education, Outreach, and Communications for the National Science Foundation's National Solar Observatory, and she's located here in Colorado. Claire is a solar physicist and a science educator and originally from Dublin, Ireland. She's here to share her love for our closest star, the sun, which we can actually see today because there's no smoke in the air. And she's also dedicated to providing equitable opportunities in STEM, which is science, technology, engineering, and math careers for students from all walks of life, especially those who are underrepresented in astronomy. We'd like to welcome Dr. Claire and take it away.
Thank you so much, Cece, and thank you everybody for joining us this morning. Yes, we're very lucky that the sky is finally cleared after a rough few weeks there, so hoping to get out and enjoy some vitamin C later on today. As Cece mentioned, my name is Dr. Claire Raftery, and I'm at the NSF's National Solar Observatory, which is the institute responsible for building the Daniel K. Inouye Solar Telescope, which you can see down here on the bottom. But today I'm going to touch on not only the Inouye Solar Telescope, but also the two other revolutionary instruments that have been launched in the last few years dedicated to studying our sun, and that is ESA and NASA's Solar Orbiter and NASA's Parker Solar Probe. But before I do that, I want to give a special shout out to Catherine Limpesi, who was my intern for a while this summer, and she played an important role in helping me put together this presentation. So thank you, Catherine. So the Inouye Solar Telescope released its first images from the new telescope earlier this year. I'm hoping that many of you saw these videos that we released early in January. And these are really quite spectacular and transformative videos and images that we got from this telescope that we're going to unpack a little bit today. So before we go further, this is going to be a little bit of a participatory presentation today. I want you all to find your local comment or chat box wherever you're watching and tell me, what does this remind you of? What do you see when you see these pictures and these videos? We had all kinds of comparisons when we released them first, but I want to hear some of what you guys see when you see this picture. So Cece, if you see comments, feel free to chime in. I can see some on our Zoom chat here. We have boiling water, lava in Wind Waker, popcorn. Yeah, popcorn, we got a lot, especially caramel corn.
You know what it reminds me of sometimes is boiling maple syrup.
Yeah, but that is good. Honeycomb is one that it really reminds me of. We've had some also pretty unusual ones. We got like skin cells on the back of your hand, and actually, yeah, and fish scales. That's another one. So
that'd be pretty dry skin, wouldn't it?
I know. It's like in Colorado, right?
Mm-hmm.
So yeah, these images remind us of all different kinds of things, and not necessarily the surface of our local star, but we're going to walk through why that might be the case today. So first of all, I want to put them in context. This picture here, the full yellow picture, the yellow disk, is a photograph of our sun taken with the National Solar Observatory's other network of telescopes called GONG, and this is a series of 6 telescopes spread all over the world, so it means that we always have eyes on the sun. We're always able to see the sun at all times. So that's the full disk picture in the background, and you might be able to see some little prominences and other features on the edge of the sun at that time. And then in the middle of this, you can see that picture that we were just looking at from the Inouye Solar Telescope. And you can see that this is actually quite a small fraction of the solar surface. It's a pretty small region of the sun that we're able to see with this telescope. And in that case, it's a bit like a microscope. So we're able to see a very small region, but in very, very high definition. And that's what makes it really, really special and effective. But the downside to that is that you're unable to see the full disk of the sun in that resolution because excuse me, if that was the case, it would be such a large image that we would barely be able to process it. So in here in the center of the sun, we can see this snapshot of the Inouye Solar Telescope image. And because it's such high resolution, we're actually able to blow this up to see even more detail. So this expanded region here, this is 7,000 by 7,000 kilometers. So it's kind of a meaningless number. It's hard to really put that in context. But to give you an idea, that means that one of these larger blobs is about the size of the state of Texas. And the smallest details that we can see in this picture are about the size of the island of Manhattan in New York. So that gives you an idea of how much detail that we're really seeing here. And we've never seen anything like this before. All of the pictures that we've had of the sun's surface before, especially this detail in the middle here, you can see this maple leaf looking thing. All of that is blurred out because the telescopes don't have high enough resolution to be able to see them. And so this is really transformative. This is showing us details in the cracks of the sun's surface that we have never seen before and can't fully explain yet. This is a big part of science. As we see something, we figure out what it's telling us, and then we continue to refine that process until we know for absolute sure, or as sure as we can get in a scientific laboratory setting, that is actually explaining what it is that we can see. And so until now, we haven't been able to see these kind of details. So we didn't know we had to explain them. And so this is really where the Inouye Solar Telescope is going to push the science of our sun into a whole new regime. Is we see all this new detail that we haven't seen before, and now we have to explain it. So we're going to put this in a little more context. So I said a moment ago that the smallest details that we can see in this picture are about the size of the island of Manhattan. So what does that really mean? How do we picture this in our head? So if we take the island of Manhattan and we put it back in context of the Earth, and this is an animation, I hope it runs smoothly, but if not, hopefully you can still keep up with the general gist of what I'm talking about. So if we put Manhattan back in context of the Earth, so back in its place on the globe, and then we take the entire planet Earth and we put it in context of our solar system. So the Earth is 150 million kilometers away from the sun. And of course, this image is not to scale on my computer screen. That would be pretty tough to do. We wouldn't be able to see the Earth at all. But it gives you a perspective on how tiny that island of Manhattan might be. So if we flip it around now, and instead of us sitting at the Earth looking at the sun, let's say we were on the sun looking at the island of Manhattan from all of that distance away, and how small that is by comparison to the size and the distance of our sun. And so that's the level of detail that we're finally able to see. And so for comparison, the previous largest publicly funded telescope was able to see things on the order of hundreds of kilometers and not 25 kilometers, which is what the Inouye Solar Telescope is able to resolve. So this is a really exciting time for people studying and observing the surface of the sun. So that means that all of these bright points, these bright spots that we saw in the video earlier on, these are all on the order of the size of the island of Manhattan. So it's really sort of mind-bending when you think about it like that, because you look at these things and they look really small and fine scale detail, and then you realize that they're the size of a major city in the United States. And so we're looking at crazy scales that really don't make sense to us here on the planet Earth. But what are we seeing? What is this sort of bubbling caramelly mess that we can see in these pictures? So again, I want you to jump onto the chat and I want you to tell me what you think these three videos have in common. So on the left-hand side here, we have a cup of miso soup. In the middle, we have those pictures from the Inouye Solar Telescope of the surface of our sun. And on the right-hand side, we have a bowl of vegetable oil being heated, and we've put some glitter into it to really enhance the patterns that we see in there. So what do you think these three different systems have in common? So one of our comments here is different densities and temperature absorption in those different material densities. Yeah. What else might these be seeing in common? Any comments from our other platforms? Ken is giving the answer away over here. They all form the same cell shapes as they boil. Yeah, that's a great observation. Okay, so the answer that Ken Carpenter got was it's convection. All three of these systems are demonstrating the same mechanism for transporting heat from one area to another, and that is the idea of convection. And so this is something that we see all over the Earth anyway, but also throughout our solar system. So where else do we see convection? Again, if you want to jump on the comments and type in some ideas, some of the important places that we see convection on the Earth. One is the big body of blue liquid stuff covering the planet. We see convection patterns in our oceans, yeah, geothermal cavities, volcanic lava. So basically anywhere where we're seeing this heat transfer between liquids and gases, we see convection patterns show up. So again, I hope this video plays smoothly for you, but if not, I've put the link to the original on the video if you wish to look at it later. The credit for this video goes to the Singing Zoologist on YouTube, so thank you so much for putting this wonderful demonstration together. So this demonstration is showing us the motion of convection from the side. So what we see here is a cup full of hot water, and it is sitting underneath a plastic box that has tepid water in it with some different color food dye. So we have red and blue food dye that's just sitting on the base of this box. So as the heat from below, the heat from the cup is heating the water nearest the cup, and it's causing it to expand and rise. And as it rises, it starts to lose its heat to the outside air. And as it loses its heat, it then starts to sink again. And so this creates this circular motion that we see. Hopefully, again, it's moving smoothly for you in this demonstration, but you see these big cellular type structures forming called our convection patterns. And this is very similar to what we see on the sun. But how do we transfer this to the sun? So let's quickly have a step through the anatomy of our local star. So if we begin on the inside, this is the core of the sun, and it's the energy in the core is generated by nuclear fusion. And so this is where the sun's energy is coming from, is inside deep in its core. And when that energy is generated, it has to go somewhere. So it is leaving the core and moving towards the edge of the sun. And first of all, it passes through the radiation zone. And so this is sort of the majority of the inside of the sun. And it is so dense that light leaving, or energy particles leaving the core of the sun, can take up to 1 million years to get to the outer layers of the sun. And that's because every time the particle tries to move, it will just bump into a new particle and have to change its direction. So instead of going in a straight line, it does what we call a random walk, and it can take a very long time for the energy particles to make it out towards the outer layers of the sun. But when they eventually do, they meet what's called the convection zone. And this is an area, it's like a shell of the star on the outside, where the densities are changing. And so the energy and heat that have made it from the core through the radiation zone then meet this new zone called the convection zone, where heat is transported exactly like we saw in the video previously, where the plasma near the edge of the radiation zone, so the bottom of the convection zone, so right here, this gets heated, it rises up towards the surface where it loses its heat to the upper layers, and then it falls back down again and it gets heated, and you end up with these big circular patterns, which we call granulation. And we see the effects of this granulation on the solar surface. So this is very much an artist's impression. This is not truly what it looks like, but this is what we're seeing when we look at the surface of the sun. We see these granulation patterns, these big cells. Now, I want to remind you again of the scale of these. So we said earlier that one of these cells is about the size of the state of Texas. So that means that the heat is rising up through the middle of Texas, and it's taking the entire state for it to be transported, lose its energy, and fall back down again. And so this also can tell us something about the depth of the convection zone, because we can understand the physics that causes this to happen. So it tells us how deep this area of the sun is. And so this is partly how we were able to investigate what's inside the star, even though we can't see it directly. And so we've talked a little bit about the inside of the sun, and now I want to shift to the outside of the sun, this area out here, this is called the solar corona. And this, honestly, in my opinion, is one of the most interesting parts of the sun. And the corona, not in this case the coronavirus, for us this was very unfortunate naming, but we're talking about the outer layers of the sun that are caused by solar magnetism. And so if you can imagine that this picture here is a bar magnet. So if we had a bar magnet that was lying over the sun's surface and it was showing what you might have done in middle school or in high school, where you see iron filings sprinkled on top of a magnet and you see almost like a butterfly effect. Well, this is very, very similar to what we see on the sun's surface, except that we have all of this stuff around here, all of these loops and all this messy structure that is not representative by a simple bar magnet structure. And that's a talk for another day, but that's caused by the winding up of the solar magnetic field inside the sun. And then eventually it gets so wound up that it bursts through the surface. And we see these big loops forming in the solar atmosphere. And we'll see some of them in just a few minutes. But where those magnetic loops burst through the surface, we see markers of this on what we call a magnetogram. And that's this gray and black and white picture that we see here. This is called a magnetogram. And it's a picture that represents the magnetic field direction and strength of the solar magnetic field. So where we see black and where we see white, this is where the sun's magnetic field is coming in and out of the solar surface. And where we see gray, either there's no magnetic field or the magnetic field is going parallel to the surface, so we can't take a proper reading on it. And so this is a really important way that we can measure what's going on the sun's surface. And it's a really key part of how the Inouye Solar Telescope is going to take its measurements. But first of all, we're going to jump back into the comments section. So pull up your chat window and tell me what you see in these pictures. So these are pictures of real videos from the sun, from the GOES SUVI instrument, courtesy of Dan Seaton. And so take a second to tell me what the first thing that jumps to mind when you see these pictures. Take a second to give everybody a chance to respond. Fuzzy limb, yeah, it's not a clear cut off at the edge of the sun. Yeah, it's generally fuzzy looking. It doesn't have as much structure as we might imagine. The explosion in the top left, yeah, so this is a big one, right? Looks a bit like a filament light bulb to me. And not only that, but you can see that there's this brightening happening underneath the explosion right here. So this is what we call a solar flare, and that's the release of light and heat energy during a magnetic explosion. The emission of this stuff up here in the top left, this is called a coronal mass ejection. And that's the stuff, that's the material, the atoms and molecules of magnetic field. And so that's an important distinction between solar flare and coronal mass ejection. One is energy based and one is material based. Is there another eruption at the lower right? Let's have a look and see. I don't necessarily see an eruption, but I do see a nice bright spot here. So these bright spots, we call them active regions, and they are the bright areas that sit above sunspots. And so when you look at sunspot pictures and active region pictures, these are those loops that I mentioned where the magnetic fields come out through the surface and up into the atmosphere, and they actually trap million-degree gases along these magnetic field lines, and those gases glow really brightly, and that's why we see these loops. So how about this side here? So it's a similar but different picture. We can see something happening on the right-hand side. So this is another picture also from the GOES 16 SUVI instrument, and we have a really big loop coming out here. It bursts, it explodes off to the right hand side, and then we see all of this bright stuff showing up. These are our flare loops, and we can see this sort of spiky, pointy structure right here. And this is, we believe this is where the what remains on the sun actually remains tethered to the eruption that's going out into space, and it's getting pulled out. And eventually that will break, that won't stay forever. But this sort of pointy structure is a really interesting thing around magnetism and studying magnetic fields. The other thing I really want to point out to you here is right after the eruption, or as the eruption is happening, you'll see a wave traveling all the way across the sun. and this is called an EUV wave. EUV is ultraviolet, extreme ultraviolet waves, because we see them in extreme ultraviolet light. We wouldn't see this in many other wavelengths that we can study the sun. So I'll let it play one more time. And so the thing that's sort of mind-blowing about this for me is the amount of energy that must take to cause a shockwave to travel all the way across this picture. So for context, the Earth is about the size of this bright spot. The Earth is really small. So can you imagine how much energy it must take to cause an eruption to travel all the way across the sun to that degree, and how much energy must be involved in these eruptions? So this is some of the benefits and really interesting side of studying the solar corona. That's the fuzzy outer layer of the solar atmosphere, is the corona. And this is what's happening. All this dynamic behavior, you can see these loops wobbling and waving up here. You can see some more structure down here. You can see a little circle. And all of this tells us about what is happening with the sun, and specifically with the sun's magnetic field. That's really where a lot of the keys to the sun's behavior is held, in understanding the sun's magnetic field. And so together, the Inouye Solar Telescope is going to be working very closely with two new instruments I mentioned earlier, called the Parker Solar Probe and Solar Orbiter. So Parker Solar Probe was launched 2 years ago from Kennedy Space Center, and this is a NASA mission that is headed towards the sun, and is actually going to get relatively close to the sun. And Solar Orbiter was launched in February of this year, right before the pandemic hit. And this instrument won't get quite as close to the sun, but will be able to study a whole different swathe of the sun's behaviors. Whereas the Inouye Solar Telescope is earthbound. It's a ground-based solar telescope, which is being built in Maui in Hawaii. And it will be studying the sun's magnetic field overall, as well as the sun's sort of dynamic behavior in support of what Parker Solar Probe and Solar Orbiter will see, which will be much closer up, but they won't be able to see the full context of the sun. So these three together are really creating a unique way to observe the sun and to understand some of that behavior that's happening out in the solar wind, which is that area past the solar corona. So first of all, I'm partial to the Inouye Solar Telescope. The National Solar Observatory, which is the organization that I work for, is responsible for building and operating this telescope in Hawaii. So even though the telescope is based in Maui in Hawaii, our headquarters are actually right here in Colorado. So we're in Boulder on the CU Boulder campus. And this is where most of our science and engineering and administration and so on is done. So this is where I'm based. I live just outside of Boulder in Louisville, and that's where I'm calling in from today. So this telescope is located at 10,000 feet, and it is it's near the summit of Haleakala in Maui, and it is the largest solar telescope that has ever been built. And we're going to step through to figure out why that is the case. So this is a schematic of the telescope. This is a cartoon that was drawn by one of my colleagues, and you can see that, well, I'm going to zoom in first of all. Here we have the entrance aperture. So this is where the sunlight comes in. This is a 4-meter entrance aperture. So the sunlight comes in through this hole in the dome. This circular area here is called a dome. The light comes in and it hits our 4-meter primary mirror. So this mirror at 4 meters, it's about 13 feet, is the largest mirror for a solar telescope that's ever been built. And by comparison, the next largest mirror for a publicly funded, so not a university telescope or a private telescope, so the next largest mirror is 0.76 of a meter. So we're going from 3/4 of a meter to 4 meters. So you can imagine what a difference this makes to us. And the big difference is in resolution. By being able to catch more light, we're able to see much more detail and resolve to much finer details that we've seen in some of those early pictures. So once the light comes in through the aperture and bounces off our primary mirror, it moves up here to our heat stop. And this is a really important part of the telescope, and it's where a lot of that excess heat that you can imagine is gathered by collecting 13 feet worth of solar light in a very intense way, focusing it on a single spot. This is where a lot of that excess heat is removed from the system, which makes sure that our optics later down the optical path are protected and that they are not in any danger. So once it passes through the heat stop, we hit the secondary mirror, which is in this box right here, and then it passes through another series of mirrors down through the telescope into what we call the Coudet lab. So unlike most astronomy telescopes, which attach the instruments right up here at the telescope level, that's not what we do here. We pass the light down into a whole separate room, and this room actually rotates with the sun. So as the sun moves across the sky, it appears to rotate in the sky. And so in order to make sure that we have no blurring happening as the telescope moves, we move the entire room underneath it to compensate for that rotation of the sun. And so this room rotates very slowly throughout the day to compensate for that rotation. So as the light comes in here into this room, it's passed into up to 4 different instruments at the same time. So we have 5 instruments that will be based in this room, and 4 out of the 5 can work together to see the sun and study its different properties at any given time. And sitting just outside of this room is our instrument room. So this is where our telescope controllers will be, our telescope operators will be located. So this is a clean room, it's a safety room, and it has a window that they'll be able to look through, so they'll be safe, because you can imagine there's a lot of very high intensity energy bouncing around this room. And so this makes sure that the operators remain safe, but they can also see what's happening at any given time, and they make sure that everything is safe and under control at all times. So this is just a picture of the actual telescope when it was under construction. So this is not yet at the observatory. This is where it was being built. And just to give you an idea of the size of this and how big it is as it moves through its system. It was built by Ingersoll. I can't remember exactly where they're located, but the company was called Ingersoll. So they took this video for us. So for context again, this is where the primary mirror sits, where this concertina is, and this is 4 meters, so 13 feet. I'll just give you some context for how big it is. And then these are some pictures of that structure inside the telescope. So again, for context, you can see a person here, and just how big this actually is. This is our 13-foot aperture up here at the top. This is our primary mirror, so you can see all of the electronics on the back here. This helps to push and pull the mirror to compensate for any issues as a result of gravity or some of the really large scale atmospheric effects. We have an adaptive optics system further down the line that help accommodate the small scale adaptive optics. And then up here, this is where our heat stop and our secondary mirror is. So this is an unusual telescope because it's what we call off axis. Normally, a secondary mirror would be directly in line with the primary mirror, and you bounce your incoming light off of the primary and straight into the secondary. But because we want to be able to image the solar corona, you have to make sure that your light beam is as clean and clear as possible. So we've had to move the secondary mirror out of the light path of incoming light to make sure that that's as clean as it can possibly be. And then this is a picture from the primary mirror looking up past the secondary towards the entrance aperture. And this is it from the different directions. So this is the secondary mirror, this is the heat stop and secondary mirror system up here. And then this is our mirror, a primary mirror down there. Okay, so then NASA's Parker Solar Probe and ESA's Solar Orbiter I mentioned are working in conjunction with the Inouye Solar Telescope. And these are 2 satellites. These 2 satellites are in space. Parker Solar Probe is moving its way closer to the sun every time it passes an orbit. I have a video that will show you some of this in just a second. And Solar Orbiter is also making its way close to the sun. And so the idea here is that these, Solar Orbiter in green right here, and Earth is where the Inouye Solar Telescope is located, of course, and then Solar Orbiter in darker green. So we have teal and green are the 2 orbiting satellites. The idea here is that by sending probes close to the sun, they can do what we call in situ measurements. So this is capturing particles right where the observatories are located, as opposed to looking far away. So this would be the difference between taking your temperature by putting a thermometer under your tongue versus using an infrared camera to take a picture of somebody from far away. And so by combining that skill by moving towards the sun with the remote sensing that the Inouye Solar Telescope will be able to do, we're able to capture a much more detailed understanding of what's happening, especially in the sun's corona. So you can see that these telescopes get closer and closer, the solar orbiter moving right into the inner orbit of the sun right here. So that is pretty much what I wanted to talk about today. I am more than happy to take questions. Oh, I apologize. Please ignore this right here. I'm more than happy to take questions and chat more about the telescopes or features of the sun. And in the meantime, I have this gratuitous video of beautiful solar eruptions taken mostly with the Solar Dynamics Observatory, which is a NASA instrument, the AIA instrument on that telescope. So thank you for having me today. I'm delighted to be here, and I will happily take questions.
Well, while everybody is waiting, and I encourage everybody to type your questions in wherever you are so we can get them transferred to the chat here. I have a question for you, Dr. Claire. I want to talk about the nano flares. Do you guys look for evidence of those? Are they really a solution to the problem of the coronal heating?
Well, I can't say for sure whether they're a solution to the coronal heating problem. If I could say that, I might get the Nobel Prize. But the Inouye Solar Telescope will be really well situated for seeing nano flares, because we're able to see the sun's surface and atmosphere at such high resolution. And in such small scales, this will be a perfect opportunity to capture nano flares. So for folks who are not familiar with the idea of nano flares, these big eruptions are called solar flares, but they happen on much smaller scales all over the sun's surface. So you can kind of get an idea of some of these blipping around in what look to be kind of quiet areas of the sun. So these little blips around here. And so the theory is that these flares together are powerful enough to heat the solar atmosphere. Something I didn't talk about today is that the solar surface is at about 5,000 degrees Kelvin, but we're talking about such big numbers, the unit matters very little. So at about 5,000 degrees at the surface, but the atmosphere of the sun, the solar corona that we're seeing here, is more than 1,000,000 degrees, and we have no clear understanding of why that's the case. There's two major theories, and nano flares are one of the theories. And so we actually hope that the Inouye Solar Telescope was going to go a long way to justifying or rebuking the nano flare theory. So yeah, fingers crossed that this will be something we'll have a decent answer to in the next few years. So I see some more questions in the Zoom chat. Will I read them out and answer them?
Sure, go unless you want me to.
I can read these ones. So different telescopes, the question from Nick is, different telescopes gather different data from the sun, X-ray, gamma ray, infrared, etc. Are there dedicated telescopes for all of these, specifically for the sun? Yes, absolutely. So the pictures that you're looking at right now are extreme ultraviolet. These are images taken with the Solar Dynamics Observatory, which is really focused mostly on extreme ultraviolet imaging, although they also have some visible imagers as well. So I would say the trend is that most telescopes either have a single focus, or they might be able to see two different wavelengths that are close to each other, because the way in which you have to image the sun is so drastically different across the solar spectrum. It's very difficult to combine hugely different wavelengths in a single telescope. So the Inouye Solar Telescope, for example, will be able to capture light from the visible part of the spectrum and the infrared part of the spectrum. The Solar Dynamics Observatory that you see here is the visible part of the spectrum and the extreme ultraviolet part of the spectrum. There is it's recently been retired. There was an X-ray satellite called RESI, and it focused on X-rays and gamma rays. And so the reason that you have to study X-rays and gamma rays in a very different way is because the X-rays and gamma rays are so powerful that they would just burn right through any regular telescope camera like we would use to capture ultraviolet. And so we have to use a very special mechanism where you actually use a series of rotating collimators that cast a shadow on detectors, and that shadow you can use for your transformations to reconstruct where that shadow came from on the sun. And so you can't directly image these, you have to kind of recreate them. Although there is a new satellite, a new telescope called Foxy, which is coming up, that uses focusing optics to be able to image some X-rays as well. So not only are there different telescopes to capture different types of light, so very, very different mechanisms for capturing that light also. I didn't mention radio waves. So the sun produces radio waves as well. It produces light across the entire the entire electromagnetic spectrum. And so on the other end, the opposite end to X-rays and gamma rays is radio waves. And so we use planet-wide telescopes to be able to study radio waves. There's a system called LOFAR, which has radio dishes located in a bunch of different countries across Europe. And those dishes can be combined together to study the sun and other astronomical objects as a single entity, using a system called interferometry. And so it doesn't matter that they are, whole countries apart. The radio waves are so long that it acts like that's just a single detector, which I think is just an amazing understanding, an amazing thing to be able to do. So yes, the answer to your question in a very long-winded way is yes. So there's another question here on Zoom. In space, heat dissipation is a big problem. On the large Earthbound telescope, you have heat arresters. How do they do that in space for the solar telescopes? So even on Earth, actually, that's a really big deal for us. We have 7 miles of coolant, 7 miles of piping for coolant across the entire solar telescope, the Inouye solar telescope, in order to make sure that it doesn't overheat and it maintains not just a safe temperature, but a very stable temperature. Because we want to be able to capture very high resolution observations, we have to make sure the temperature stays very stable, because big temperature fluctuations will have an impact on our cameras and our instruments. But in space, they have to use even more innovative ways. So the Parker Solar Probe, for example, has a big heat shield that faces the sun. And so it is building up heat to many hundreds, I would imagine, probably thousands of degrees. And meanwhile, on the night side, so the side away from the heat shield, from the sun, behind the heat shield, is below freezing because the heat shield is that powerful. So it is a combination of really innovative engineering and lightweight engineering as well, because of course you can't put something very heavy if you're going to be launching it into space. It has to also be lightweight. So I know that's how the Parker Solar Probe is protecting itself, as its big heat shield on the front side of it. So it's a great question though. So another question here. Please give us a feel for the different characteristics that each part of the spectrum reveals about the sun in terms of temperature, magnetic field strength, etc. So that's a great question. So if we start from the radio end, the radio part of the spectrum, which is the long wave part of the spectrum, that tells us a lot about particle acceleration. So we predominantly use radio waves to study eruptions in the solar corona, so coronal mass ejections and other shock-driven features. And so that tells us about where high energy particles might be located inside of shocks coming from the sun. And that's really important for an understanding of space weather, which is the impact of the sun on Earth and how that impacts our atmosphere, our electrical grid systems, our radio communications, our satellite communications, and so on. And so that particle acceleration is really important for that aspect of our understanding of the sun. If we move a little bit further down the spectrum, past microwaves and into the infrared region, understanding the infrared part of the solar spectrum is actually not something that's been done a whole lot. So the beauty, one of the things that's really great about the Inouye Solar Telescope is that it's going to have a dedicated instrument called Cryoneers, which is going to study the area of the sun's atmosphere, which is sort of this region right here, but in much greater detail than we've been able to do before by using infrared observations. So the hard thing about infrared is that it gets interfered when you have any kind of other heat source nearby. So that you have to make sure that everything is very cold. So that's why it's called cryonorous, because it's cryogenically cooled. And so it's going to focus on this area right near the edge of the sun, as well as studying the atmosphere in general. But this is where we expect to get some really new revolutions. Is that part of the solar corona where the solar wind is accelerated. So moving past that into visible light, we have a lot of observations of the sun in visible light, and for the most part, they tell us a lot about the sun's magnetic field cycles and dynamos, and we're able to use some of these observations to actually study the sun's behavior on the backside of the sun, where we can't use telescopes to see directly. We can use what we call helioseismology to measure sound waves inside the sun and measure how they're reverberating around the edge of the sun to figure out where the magnetic fields are clumping together on the backside to be able to see where the sunspots might be and where they might be rotating around the front side of the sun, and when we can expect large sunspots to arrive. Moving past that into ultraviolet, well, these pictures in this video section are all ultraviolet images, and you can see that you see a lot of dynamic behavior here. You can see these bright loops that are forming. These are coronal loops. You can see active regions. You can see a lot of behavior in the chromosphere and the corona. And then when you move into X-rays and gamma rays, you see sort of heightened versions of this. So they have less structure in X-rays and gamma rays, but you can see where all of the energy is being dumped. So if you have a solar flare, where particles are losing their energy into the atmosphere, they produce a lot of X-rays. And so by telling where the X-rays are, it tells us about the mechanisms that are causing solar flares to, the particles in the atmosphere to be accelerated during a solar flare, which can tell us about what's causing the solar flares to happen. So hopefully that about covers the whole spectrum. And we depend very heavily on these multi-wavelength observations to tell the full story of the sun. If we were only to ever look at the sun in a single wavelength, so visible light, for example, or even ultraviolet light that we see here, we would see only a tiny fraction of the overall story. So it's really important that we have access to all of these different wavelengths, so we can piece together these complex stories to understand what's driving the behavior of our local star. So another question here from Nick. Have we learned anything about other stars and with planets that we've been able to confirm through the study of our own star, or vice versa? That's an excellent question. So yes, we are able to use the sun as a template for other stars outside of our solar system. And this actually is one of the specialty areas of the National Solar Observatory. And so we are able to study the sun's atmosphere and dynamic behavior to understand how other stars might behave. And actually there is a recent study by one of my colleagues at NSO, which focused on a planet near Alpha Centauri, which is another star that has habitable Earth-like planets. And so the excitement was that this planet might be able to foster life, until my colleagues started to study this and realized that the star that this planet was orbiting was producing multiple extremely large X-class flares every single day. So many, many, many times more than what we get with our sun. And so that by itself would be enough to inhibit life from being able to form, because of the amount of radiation, high energy radiation being produced by the star. So I think that was a pretty innovative and a pretty cool thing to be able to understand. Disappointing that it may not be an Earth-like planet or habitable for humans, but also just being able to understand that not only in the search for habitable planets do we have to focus on the planet, but we have to also focus on the star and its behavior also. But yes, we're able to use the sun. The sun is the only star in the whole universe whose surface we're able to resolve, whose surface we're able to see in enough detail to actually be able to see the behavior that's happening in any kind of detail. And so by applying our understanding from the sun to these other stars, we're able to understand its behavior, its magnetic behavior, and many other things, which also tells us about its planetary behavior as well. So we use a technique, well, there's multiple techniques for observing extrasolar planets, but one of them is similar to what we see in our solar system with transits. So as a planet goes by, the light emitted from the star changes, and we're able to then tell information about the size and the chemical makeup of the planet by what we see the changes in the star's profile. So yeah, that's a great question also. So I have another question here. What kind of shielding is required to keep solar telescopes operating as they get closer to the sun? That's a great question. I don't know the exact details of the shielding used by Solar Probe or Solar Orbiter. I don't know what the material is made up of, but that's something that I can certainly find out and get back to you on. It's something that will be widely available on the NASA webpage for Solar Probe, so I'd encourage you to take a look there. I know that some of the materials that we use in the Inouye Solar Telescope, we have a few key materials. One is we use the very properties of the area that it's in. So the fact that it's in an area where there's good airflow, there's pretty steady wind, and we're able to build the dome in such a way that it actually uses that airflow, that laminate airflow, to be able to keep everything at a moderate temperature. We also use copper in the heat stop to be able to remove some of that heat from the system. And I mentioned earlier that we have 7 miles of piping that runs coolant throughout the entire telescope, and that coolant is dinylene, and so it's cooled every night by ice that's made in the just outside of the telescope in the support building nearby. We make a swimming pool's worth of ice every evening overnight, which keeps the dinylene cool. Now, of course, the properties of a spaceborne telescope are going to be very different because they have to be lightweight and compact, and the conditions are quite different. But like I said, I'm not as familiar with those at this point in time. So another question here is, how big would a telescope's mirror or aperture need to be in order to resolve the surface of the next closest star? Oh boy, that is a great question. I don't know that I could tell you that off the top of my head, but if you give me a few minutes to do some math, I might be able to figure it out. Well, I guess what I would say is that right now, some of the biggest telescopes that we have are, tens of meters, 20 meters across, and for nighttime purposes, not for daytime astronomy, and they're still not able to see them. So my guess would be, many tens of or even hundreds of meters in diameter to be able to work that out. But I'd have to sit and do some mathematics to figure that out off the top of my head. So does the work you do give insight into the evolutionary stage the sun is in? So that's a really interesting one. There is an analogy that I like to kind of ponder when I'm thinking about this. So maybe some of you have heard of the Hertzsprung-Russell diagram or the HR diagram. This is basically a picture, an evolution of a star, the star's life as it goes through from birth to death, and it sort of helps to understand different types of stars and where they are in their evolution. So you have, hot blue stars and you have older red stars and how they evolve. And the sun capture is captured just at one instance. And so the way I like to think of it is, if an alien species came to Earth and took a snapshot of the human race, just 1 second snapshot, if we look at any one human, we would know relatively little about the human race from that one human, because it would be at a single instance in their evolution. So they might be a teenager, and so we wouldn't know how long they live for, or how long they've been alive at that point, or how tall they might get, or whether they change hair color throughout their lifetime, or any of the other fundamental properties of humans. However, if in that same instance we were able to see a snapshot of all of the stars all of the people on the entire planet, then we'd have a really good understanding of, well, humans live about 100-ish years. They tend to be somewhere between 4 foot and 6.5 foot ish tall. They tend to be so big, so wide, different color hair, but they're limited to these major hair color groups, and then we have a few outliers where we have people with pink hair or purple, but they're pretty unique and they're not part of the mainstream. And so we're able to piece together a much better understanding of how the human race behaves. And I think the same way of our understanding of stars. So even though we might live as an individual for 80 to 100 years in our own lifetime, that's a blink of an eye in our understanding of different stars. And so in order to understand the evolution of these stars, which live for billions of years, we have to study the entire universe and look at all of the different stars across the entire universe to see what those scales are. And so the sun plays a key role in that. The sun actually is pretty average. It's not all that special. It's pretty mediocre in size. It's a pretty standard G-class star. It's not too hot. It's not too cold. It's right in the middle of its lifetime, so it's lived about 5 billion years and it has about 5 billion years left to go. And so, you know, maybe that's why it can support life at this time in its evolution. And so understanding how that fits into the bigger scheme, I think, is a really important part of how we see the universe. So yeah, thanks for giving me the chance to tell that story about the human race. I think that's a great way to picture how we see the rest of the solar or the rest of the universe. So there's a few more questions here. Let me see. So Ken is saying that a solar type star needs about 500 meters to see active regions. So there you go. So if a solar type star had 4 parsecs, we would need a telescope 500 meters in diameter to be able to resolve its surface. So thanks, Ken, for doing that math. That's great. So another question here, what kind of maintenance do you have to do to keep the Inouye Solar Telescope mirror clean, and what's its coating? So actually that's a really timely question. The telescope is in preparation for being removed from the telescope. The mirror is going to be removed from the telescope, and very nearby, so just across the parking lot, is another telescope that's run by the Air Force. And inside of that observatory, they actually have a mirror coating chamber. And so they're in the process of preparing to remove the mirror from the telescope to bring it across to have it recoated, because it's been on the telescope during a heavy construction period. So of course there's, you know, dust and other kinds of contaminants that have landed on the mirror. Even when you're very careful, that's inevitable from just being in the site. And so they're going to remove that and have it cleaned before we start our full operations. The telescope technically will continue in its construction phase until the end of the year, the early new year. Unfortunately, things got delayed by the pandemic. We had to go into shutdown and stop construction for a few months. And so construction has restarted, but it will take by adding in social distancing requirements and so on, it's going to expand how long it's going to take to get this last period of time, or sorry, this last period of construction completed. So back to your original question. There is a pretty complex system that takes the mirror off the telescope using a crane, and then they can move it across to the coating chamber at the Air Force. And they wash it very, very carefully, and then it's coated in a really, really fine layer of aluminum. So it's on the order of microns and how much aluminum there is. We actually have a blog post on this if you'd like to take a look. www.nso.edu/blog. And we have lots of updates and stories about the telescope and the other things that are going on at the National Solar Observatory. And we have a story about that when they were coating it for the first time and how all of that went about. So yeah, that's a great question and very timely at that too. What are some of the most interesting solar citizen science projects you've seen? Oh, that's interesting. So there's a few citizen science projects going on. So one of the widest reaching ones that I know of is called Aurorasaurus, and it's a project that focuses on citizens noting when they see signs of aurora in the skies above their house. And then they're able to use that data to feed back into the measurements from magnetometers and observations of aurora in the sky to be able to improve modeling understanding of what's causing the aurora. So, excuse me, I should say explicitly that the aurora is caused by the sun, and that's not something everybody's familiar with. So as a result of both solar wind flowing towards the Earth, but also eruptive events like coronal mass ejections. Energy from the sun is dumped into the atmosphere of the Earth, but it doesn't happen all over the atmosphere. It travels along the Earth's magnetic field and gets poured into the polar regions. And as that energy is transmitted from along the particles that are along the magnetic field into the atmosphere, it causes the atmosphere to glow and to produce multiple colors. So the colors that we see in the aurora are connected to the different atoms that are in the Earth's atmosphere. And so they glow at different levels and different areas because of how dense they are at that particular height in the atmosphere. And so Aurora Soris uses people's observations of the aurora to be able to do this. Two other citizen science projects that were timely, so they're not continuous, but they were really impactful, are the Citizen Kate project and the Solar Mega Movie project, which were run during the solar eclipse in 2017 and will hopefully be rejuvenated for the 2024 eclipse in a few years' time, which, if you're not familiar, will run from Texas to the northeast coast. To New England. And so start planning now where you're going to make your way to go see this eclipse. So the Citizen Kate project had groups of citizen scientists who had research level equipment scattered all the way along the path of the eclipse to take a continuous set of observations coherently across the path. The Eclipse Mega Movie project used people's amateur pictures, like with their cell phone or with if they have their own solar telescope or camera, and they pieced those pictures together into a continuous movie in a similar sort of a way, but using the equipment that people just had to hand themselves rather than a dedicated set of tools. And so on the one hand, the Citizen Kate project allowed for more sort of cohesive video and movie and understanding of the science that's going on behind that. It was limited in how many people could participate. The Solar Mega Movie allowed more people to participate because you didn't need more equipment, but it was slightly harder to piece it all together with the different types of equipment that people did actually use to capture that. So both had their virtues and both were able to add significantly to the understanding of that acceleration region of the solar wind. So that was also pretty interesting as well.
So yeah, I just want to step in here and say that we had a number of people working on the Solar Mega Movie and the Citizen K project from the site where we were observing in Wyoming for the eclipse. It was pretty interesting. How many people were involved in that?
Oh gosh, I would say hundreds. There was 48 sites for Citizen Kate, and each site had probably 5 or so people involved. So at least 100 people. On top of that, we had interns who were helping with the coordination, and we had statewide leaders who were helping to make sure everybody was trained. So I would guess about 150 people for Citizen Kate, and I think there was many thousands involved in the Eclipse Mega Movie project.
So what are the next? We're going to have to close in a minute, but I do have one other question. Sure. What are the next steps for the National Solar Observatory? You're going to be resuming construction. Are there any other projects that you've got ramping up for the future?
Yeah, we have an exciting development hopefully coming up. It hasn't been confirmed yet, but we are working towards it, called NG Gong. So I mentioned earlier on that we have a network called the Gong Network. It's a global oscillations I can't remember what the NG network group, Global Oscillations Network Group, and it's a series of 6 telescopes spread across the world in order to be able to study the sun. And that network was built 30 years ago, I think, or more. So it's somewhat out of date, and so it's ready to be upgraded. And it's a really key part of space weather observations, which are done through NOAA at the Space Weather Prediction Center. And so we're looking at trying to ramp up to renovating the NG Gong network and putting in more cutting edge technology and observations in there, and being able to really focus on ground-based space weather observations of the solar atmosphere. And so the nice thing about that is that, unlike the Inouye Solar Telescope, which is the microscope concept, which is very detailed in a small part of the sun, the Gong network is the full sun at lower resolution, so you're able to see it, the whole sun evolving in more real time. And so that hopefully will be the next few years. But we're still in the ramp up phase of the Inouye Solar Telescope also. Like I mentioned, construction won't finish until the spring of next year, early next year. And then at that stage, we'll start observations and hopefully get many more spectacular pictures like we've seen earlier today from that telescope. And between that and the solar probe and solar orbiter, really push our understanding of how the sun is working and what's driving it into a whole new level.
That's all pretty amazing. I've been following it through your colleague, John. And of course, some years ago, I worked on a project about space weather for MIT Haystack Observatory. So I've had a natural interest in that for quite a long time. Well,
Great.
thank you, Dr. Claire. This has been fascinating. And you are going to be back this afternoon at 1 o'clock with our next science activity, where Dr. Claire, Dr. Ken, Dr. Aaron, and I will be there to answer all your science questions at the Ask Me Anything Science Rules session. So we invite you to bring your questions about stars, the sun, planets, galaxies, gravitational waves, dark matter, dark energy, astrobiology, life elsewhere, whatever it is that fascinates you about astronomy and space science. So we'll see you again at 1 o'clock here, and thanks for coming. Thank you, Dr. Claire.
Thank you, everybody. Thanks for having me.